Hello, ladies and gentlemen. Herzlich willkommen, добро пожаловать, друзья. My name is Andrei, and in this video I would like to do an OpenFOAM calculation of the Mercedes Benz w126 series. The mesh for this model we have already done. Please check for it videos advanced meshing with SnappyHex mesh and CF mesh for Fluent, Star CCM Plus and OpenFOAM Part 1, Mercedes Benz W126 and Part 2. If required, please contact me. I would deliver the geometry with meshing files after the consultation. My contact details can be found at the end of this video. Generally, this calculation is based on the motorbike tutorial, so you can also watch the motorbike tutorial if needed. The simpleFoam solver is used for the calculation. Let me show you the description of it from the internet. So, simpleFoam is steady state solver for incompressible turbulent flow using the simple algorithm. Simply means semi-implicit method for pressure-linked equations. Now you know what simpleFoam means, so we can start our calculation. Which steps are necessary for the calculation? First of all, I briefly discuss the mesh in this video. Then we prepare all the files for the calculation. We start with 0 folder, then we go to constant and system folder. As soon as the system files are prepared, we can start the calculation itself. And at the end of the calculation, we will look at the results and discover the aerodynamic parameters. Let's start. I go to the folder run CFD, Mercedes Benz steady, run CFD, run 200 kilometers per hour, and here we see the run snappy folder. Here I copy the run snappy folder because in the current run directory the calculation is already finished. I will present the results from this folder, and in the copy directory I will only show the starts of the calculation process, and also I show you the mesh here. In the run snappy copy I only delete the processors because I don't want to delete the mesh. Now it's done. I rename it. Copy file. Here I delete the processors. For that I go to terminal, for example. And here I can activate the OpenFOAM and remove the processors. That is how the command looks like. Everything is done. And now I open the ParaView with the meshed Mercedes Benz W126. For that I would like to execute the command paraFOAM minus built-in. That's it. I want to show you the internal mesh. Here I create the cutting plane Now it's done, and I go to surface with edges type. At the same time, I open Snappy Hex Mesh Dict and explain how the mesh is structured. For that, I go to the system and open Snappy Hex Mesh Dict. We see castellated mesh is active. It is true. Snap and layer are also active and also true. Geometry consists of inlet, outlet, walls Mercedes Benz, walls road fine, and walls slip. The walls slip contains the side walls, both side walls with the upper wall. All these geometry parts can be found in the folder constant tri-surfaces as STL files. Let me go to constant tri-surface, and here we see the STL files. Then we see two refinement objects in the form of refinement box with refinement levels 1 and 2 respectively. I can also present these refinement objects in the paraview. Here they are. Now we switch to castellated mesh controls. Here is defined the maximal possible number of cells during the meshing process as max global cells. In this case, is max global cells equal to 20 million cells. At the end of meshing, we reach about 7 million cells. You can find it in the checkmesh log file. Here is it. Here we find the total number of cells, about 7 million cells. This number is lower than the number of max global cells, which is taken as 20 million cells. So it fits with the definitions. I also see 5 million cells for a single core, which is called max local cells. From it, I reflect that I have defined the calculation for 4 processors for the meshing. If you divide 20 million cells to 4 cores, you achieve exactly max local cells, 5 million cells. I also see this in Snappy and OpenFoam run. Here is it. Snappy Hex Mesh was running with 4 cores. For further calculations, I will of course use more than 4 cores. What is also important in the Snappy Dict is the number of cells between the levels. Here is it, and it is taken as 3 cells between the levels. This can be also seen in the geometry. For example, if you go near to Mercedes Benz, you will see 3 cells between 2 levels. The refinement levels for the edges are defined in the features section. Here you can find 0 meter from the edge and the refinement level, for example, 4. The surface refinement are specified in the refinement surfaces section. The level 4.4 means, for example, that the surface have the same resolution for both at the edges and on the surface itself. Such settings of refinement levels, where the both numbers are equal to each other, improves the quality of the meshing, because the fewer different levels defined in the meshing on the surface, the better it for the quality. For example, levels 4.4 is better than 2.4, and of course the levels 10.10 is better than 0 and 10. In the next, we see the snap control settings. These settings are standard. Then comes the definition of layers, expansion ratio, first layer thickness, mean thickness. Finally, we find the mesh quality control settings in SnappyHex MeshDict. Here they are, and as you can see from the comment, these settings are also default. This capital brings us to the end of the meshing process. Now we start the calculation. I switch to 0 folder and open all the files inside. I also shut down the unnecessary files. I close SnappyHex Mesh, maybe Snappy Open Foam Run. So we begin with K. The file K contains the predefined data such as flow velocity minus 56 in y direction, pressure is equal to 0, turbulent Ka and turbulent omega. Dimensions of K file is meter square to per second square. And at the end you can see the boundary field and the definitions for inlet, outlet, walls Mercedes Benz and walls slips as well. The next file is node. It contains dimensions, meter square per second, internal field, uniform and boundary field. I will stop briefly so you can see or take over the data from inlet, outlet, walls and so on. Omega also starts with flow velocity, pressure, turbulent Ka and turbulent Ka omega. The dimensions are 1 per second. Internal field here is uniform turbulent omega, and the boundary field can be also copied as indicated here. In the next we see the pressure. Here it is. It starts with also with flow velocity. Dimensions are meter square to second square, and boundary field looks the following. The velocity also contains information about flow velocity, pressure and so on. Dimensions is meter per second, which is understandable and quite easy to understand. Internal field is uniform flow velocity, and boundary field is defined below. Now I close already discussed files and switch to constant folder. Here we see the definition for transport properties and turbulence properties. The transport properties file contains the transport model or Newtonian and kinematic viscosity nu of the air at 20 degrees, which is equal to 1.5 E minus 5 meter square per second. The turbulence properties file consists of simulation type RAS, Reynolds average simulation. This is turbulence modeling for incompressible flows. Reynolds average simulation model defined as follows. RAS model is K omega, SST, turbulence is on, and print coefficient is also on. Now we are ready to view the files in the system folder. I will start alphabetically and go only through the necessary files. First, I look at control dict file. All information that is to be calculated and information on how it should be calculated are defined here. The solver is simpleFoam, and it starts from the start time, which is equal to 0, and stop at the end time, which is equal to 500 iteration steps. Delta t is 1, right control is equal to time step, and right interval each 100 iterations. In the end of control dict, we reach the functions streamlines, wall bounded streamlines, cutting plane, force curves, and side right. We will look at some of them in the details. I start alphabetically with cutting plane. Normally I make cutting planes myself in the GUI in ParaView, but here is shown the possibility of creating a cutting plane via dictionary. The type is surface. Right control is set by right time. Format is VTK. Fields are pressure and velocity. Surface is defined in X normal direction. Type is also cutting plane. Plane type is defined by point and normal. Point is defined by 0, 0, 0 coordinates, and normal is in X direction, so it's equal to 1, 0, 0. That should be enough for explanation of cutting plane, and we go forward. Next two files, FV schemes and FV solution, are standard and taken up from motorbike tutorial. Here you can see the FV schemes. And FV solution. I close it also with cutting plane. Now we have reached the streamlines. Here you see. What is important here is the definition of seed sample set. Here we select the y-axis and two start points with the differences only in the z-axis coordinate. Here is this difference. The number of points is equal to 40. This means we have 40 streamlines between two different corner points. The rest was taken from the motorbike tutorial and was not changed. In any case, it is important to specify the correct name for the respective streamlines function. I have defined the names as distance along the x-axis. For example, we have 0.0 and the start point is by the x-axis 0 and end point is also 0. For example, streamlines 0.6 has the points 0.6 and 0.6 in x-axis direction, and for example minus 0.3 means here minus 0.3 in x direction. These names give you a possibility to understand where the streamlines are defined. Here I close the streamlines and go over to wall-bounded streamlines. You can see another file, toposetdict. Toposetdict is not necessary in our case because we have already defined the geometry in the snappyxmeshdict and in the constant trisurface folder. For that we don't need the toposetdict. I go over to wall-bounded streamlines. In wall-bounded streamlines, we have to define the patches, distance, for example 0.001. The direction will be forward, lifetime will be taken as 100. So by uniform coefficients, we have to define the axis in y direction according to our geometry. So the start point is defined here and the end point is also defined here. These points are at the front of the car, more exactly the right front area. I can show it. So we have to go to walls Mercedes Benz. Now I activate the grid. It's already active, so I only have to define the black color as axis color for better view. And what we can see, the point start point is by x direction 1 meter, y direction is 5, here you see 5, and z at the beginning on start point is 0 and at the end on 1 meter. So you can see this area. Here's the uniform coefficients start and end point defined. For cloud coefficient, I have the point on the wind sheet. You can see the cloud coefficients, y-axis, the same as in uniform coefficients, and the point is 0 in the x direction. It will be in the center of the car. The y direction is 3.5. Maybe I can show it better here. So 0 is in the center, y direction is approximately here, and the z direction is 1 meter. So this point is exactly on the wind sheet. For patch seat coefficients, I took patch Mercedes Benz 126. Axis is the flow direction, y axis, and the number of points is 20,000. The rest is simply taken from the motorbike tutorial. So I close the wall-bounded streamlines file and now we are ready to start the simulation. To do this, I go in the terminal, activate the OpenFoam, and now I can execute the following command. So run solver simpleFoam begins with decomposer, then it contains also potential form, run in parallel, and the last command is simpleFoam, also run in parallel, and written the log file. So I execute it in the copies folder and it starts immediately. Now we will see the increasing of number of processors. We have 12 processors and it can be found in decomposer dict. We have 12 processors and the method is Scotch. Now we see the run for potential form. And here you see the simpleFoam command. So we have first iteration, the second one, and it begins to run to an end. So in control dict, you see the number of iterations will be 500 and each 100 step will be written. So let me go to the finished case, and here it is. Now I switch to ParaView. For that I open the terminal, activate the OpenFoam, close all unnecessary files and start the ParaView. I stop the calculation in copied file, close the terminal, also close the previous paraview folder and also the terminal of it. And now we have a new paraview session. Here I can see the results. So I take a decomposed case and take the internal mesh. We have already examined the meshing, so let's look at the cutting plane that was created from the cutting plane dictionary. For that I open the post-processing and cutting plane and time 500. I deactivate the foam case. This is what it's look like. We can open the magnitude case. Here we can change the color palette, for example to turbo, and rescale the speed from 0 to 70 meter per second. Let me do the scale so you can see it. The next thing I'm interested in is the streamlines. Let's open one of them and take a closer look. Here you can see how the vortices are created after the equal. Now I can take a look at the wall-bounded streamlines. This is what they looks like. You can see the lines on the windshield and on the front of the engine, which radiate from the one point in all directions, like rays of light from the sun. You can also see small swirls behind the left side mirror. Now we come to the most important point of the calculation, is the definition of a drag force and drag coefficient. For that I recommend you some videos where these elements are calculated. For that I open the Firefox browser and show you these two videos. So one of them is how to calculate projection area of a front area, and the next one is how to calculate aerodynamic forces with paraview. Drag force is defined as follows. In this equation, Fd is the drag force, rho is the density of fluid, V is speed of the fluid or object in fluid. R is the cross-section area, and CD is the drag coefficient. We calculate drag force from the OpenFOAM data in ParaView. Density and velocity are known. What we still need to determine is frontal area of the car. But first we determine the drag force. For that I have to enable the road patches and let only Mercedes Benz walls. First I go to filters and extract block. Here I define only the walls Mercedes Benz. The next step is we go to the filters and extract surface. Next thing to do is to generate surface normals. For that I also go to filters, generate surface normals. Here I have to select the following options: splitting, consistency, non-manifold traversal, compute cell normal, and piece invariant. At the end I click apply. So now I press the calculator and calculate the drag force. So as a result will be drag force, and drag force will be calculated as follows. We have to click pressure multiplied by scalars in normal y direction. Here I choose the cell data and click apply. So finally I make integrate variables and select the cell data. For that I go to filters, integrate variable, apply, and we have to choose here the cell data. The result is about 1272 Newton. With this drag force result, we can determine the necessary power of a motor to move the car in the airflow. The power is equal drag force multiplied by velocity meter per second and drag force in Newton. It means that the result is approximately 71 kilowatt only to overcome the aerodynamic drag. Finally, I determine the drag coefficient. I look for the frontal area. So, first I activate the camera parallel projection. Here it is. Then I start searching for surface. For this I need select point on D and extract the selection. This is the select point on D. I choose the area and now I extract the selection. Apply. Then I look for the transform function in filters. Transform. Here I allow 90 degrees rotation by x-axis and scaling 1.a-5 by y-axis. So the rotation in 90 degrees in the x-axis and in one y direction 1a-5 and click apply. Here we see the result in XY plane. Next step is to go to filters and do the delinear 2D with alpha 0.05 and finally integrate variables. So I go to filters, here delinear 2D, here, and by alpha I choose 0.05. I click apply and close. So this is the new result. Delinear 2D is finished and finally I integrate the variables. For that I go to filters, integrate variables and click apply. Here I have to choose cell data and here we see the area 2.23257 meters square. And now we have to define the drag coefficient. I have written the equation for that. The drag coefficient is equal to 2 multiplied by force, drag force divided to density of the air, velocity of the air or car in the air, and cross-section area. The drag force is defined as 1272. Density of the air by 20 degrees is 1.225 kilogram per meter square, meter in third potential. The velocity is 56 meter per second. Both is in square, and the cross-section area is divided by 2.232 meters. The drag coefficient is resulted as 0.3. In the internet we can find the value of drag coefficient. Mercedes Benz. Here, for example, we have the definition of it and also the value of cross-section area. Drag coefficient is equal to 0.33. For that I can say our simulation is close to the real value of the drag coefficient. The determined face area from the internet is equal to 2.17 meter square, which is also close to the determined value of 2.234 meter square. So from my point of view, we have covered all the topics in this video, and now we can proudly discuss the summary. The first thing that we looked at was the mesh. Then we prepared the system files from 0 folder constant to system folder. As a second last step, we looked at the results, like cutting plane, streamlines, wall-bounded streamlines. And finally, we calculated the drag force and Gini power to counteract the aerodynamic drag and the drag coefficient. And now we have reached the end. For those who have further questions or need support from me, I will give you my contact details. These can be found at the end of this video. I wish everyone much progress. See you in the next video. Bye bye.